So we are the experimental airship control team. Switch. I'm Luke Loswald.
I'm Caitlin Poole.
I'm Ryan Lewis.
I'm Amanda Debates.
And I'm Max Walter.
So to kind of start us off, we are sponsored by Aerostar. They are 65 years old and they were originally with Raven Industries before they split off in 2012. They are world leaders in aerospace and defense solutions, and their main goals are to enhance security and to connect the world. So a little background is a term that we will be using a lot in this presentation is LTA, or lighter than air vehicles, and that is a balloon that is lifted by a gas lighter than air. Furthermore, some yaw, pitch, and roll. So the yaw is the rotation from side to side, the pitch is the up and down rotation, and then the roll is similar to a barrel roll that you would see on a fighter jet. Furthermore, so right now Aerostar's weather balloons are reliant on wind patterns and altitude adjustments. So this is susceptible to sudden weather changes, and they are usually use pseudo steering, and that is similar to the altitude adjustments. So they adjust their balloons up or down in altitude to try to find those wind currents so that way they can somewhat guide their balloons, but this unfortunately creates a very indirect flight path, which leads us into our project motivation. So our project motivation, this project has been split into multiple phases. We are going to be in phase 1, which is to create a functional airship prototype and to begin a study of stability and control. We are hoping that our prototype will look something similar to this bottom picture. Future phases will continue development and research of stability and control and to research use in other aerospace applications. These applications include technology that should be able to scale up to a full-size model.
So our project goals all start with Aerostar. They are going to supply us with a hull that we're going to use to create this scale prototype. We're not creating the large 100-foot version that they eventually want to have. So we start with the hull that they're going to give us. It'll look similar to the main body in this diagram. And then we are going to take that and add all of our attachments to it. These are going to include the 2 main thrusters on the bottom, and then the control unit that will control these. And then we're going to add the fins on the back, which is on our empennage, which we'll get into later. And then on the empennage, we'll have motors that will help with the stability and control of the aircraft. Once we get this built, we want to be able to have a controlled indoor test flight. One of the main goals, again, is the control and stability. With the motor in the back, we're going to be able to control the yaw and the pitch. So again, the pitch is the up and down of the nose, and then the yaw is the side to side. So that's going to help us with our turning. And then a main goal is fly in a straight line without much deviation. So if we can keep that on the path as easily as possible, that's going to be good. And then again, we want to be lighter than air overall.
So as Ryan mentioned earlier, the empennage is one of the main terms that we will be using throughout this presentation. This essentially is anything at the tail end of our aircraft, mostly relating to stability. So this will include our fins and any propellers we decide to put back there to stabilize the end.
Another term we will be using a lot is the gondola, which refers to everything that is not the empennage or our propellers and motor. The gondola is usually seen on the underside of the aircraft, and it's just a box that contains everything like our battery, our sensors, our Raspberry Pi, and also our receiver. This is our review of our state-of-the-art we did, which was a look into companies that were doing work that is related to our project. And that brought us to Aerodrum Limited and eblimp.com, who both make small indoor and outdoor remote control blimps. As you can see in the top left, those are the blimps they make. They fly them around at like festivals and concerts and parades. And they are controlled using 2 main thrusters that are seen in the top right. They are connected together on a singular shaft that rotate to adjust the pitch. And in order to turn, they have one propeller spin faster than the other. And then the bottom right picture, you can see one of the empennages they have, which is just a single propeller in the back. And you can also see the fins. And these are just used for creating a more stable aircraft.
So one of the main calculations we're going to be using for this project, especially when we scale up to a full-scale model for Aerostar eventually, is the Buckingham Pi theorem. This is essentially a way to relate different variables, especially when you have a lot of them. So as you can see, we have selected 6 variables right now that may change in the future, but this relates these into 3 equations, and these equations are all dimensionless, meaning that we can just use them as dimensionless constants, and we don't have to have very complex formulas, and we can simplify those formulas for when we actually do our calculations with our values.
So our first design solution was to figure out what we need to get this thing to move. This is the hull or LTA that Aerostar is going to give us. And we need to calculate our force of drag to figure out how this is going to move. So the force of drag is any opposing motion on the direction that we are going to be moving. So we later are going to talk about where these thrusters are going to be. And right now they're going to be here-ish in the middle. And we're going to have wind and all other kind of forces opposing this thing. So we need to figure out how much force is on this while we're going at a speed of 2.5 meters per second with a coefficient of drag between 0.05 and 0.1, which is given to us by Aerostar. And when we calculated this, at going 2.5 meters per second, we got about 1.3 newtons of force or 0.309 pounds of force. And using this, we can figure out how fast our motors have to spin and how much thrust our propellers have to make that Ryan's going to talk about later. Some key dimensions that we were given from Aerostar were that we need, our hull is going to be 15 feet long, have a max diameter of 6 feet, a volume of 263 cubic feet, a weight of 8 to 9 pounds, and that is just the hull itself that they're providing us. And then the total lift with the air on the inside that makes us lighter than air is 15 pounds. And subtracting the weight that the hull already is, that gives us about 6 pounds to work with everything else that we're going to be adding on to this thing.
This is a free body diagram of our lighter than air vehicle, and you can see our drag and thrust are our only horizontal forces. So to be flying at our steady speed of 5 knots, which is about 5.6 miles per hour, we need to create a thrust that is equal to our drag of 0.309 pounds. But we are mostly concerned about is our lift and our weight. Right now, our max lift is 15 pounds and our weight is already 9 pounds. So we have 6 pounds to work with when we add all of our materials like our gondola and our empennage and all of our propellers and thrusters.
One of the design problems we're facing is how we want to attach everything to the hull without compromising the hull because it has to be able to hold the gas in it. So commonly this is done right now with patches and loops. They use like a 3M adhesive that's high in tensile strength. Stick that to the hull. Attached to that is a patch with a loop on it. To that loop, you can run a carabiner. To the carabiner, you can run a cable. From the cable, you can attach that to the outermost portion of your mast. So in our case, that's going to be the fin and the gondola. You typically use 4 cables to get a sturdy attachment. And then when you tighten these down, it presses the fin or the gondola to the hull. And then connected directly to the hull is some other form of attachment you can see here. We want to use Velcro for this, partially because it's going to be very adaptable. We can move it around and change our fin locations, which we'll get into a little more later. But yes, that is the method we're planning on using for attaching our designs.
So another thing that Aerostar wanted us to look at was making this thing as efficient as possible and as structurally sound as possible. So the more fins that you add to this, the more statically stable it's going to be, but it also decreases in efficiency. So the least amount of these things is going to be the most efficient for us. Our main goal was to have these be removable and super easy to work with, and they need to be adjustable so we can move them wherever we want to have them. And this is going to benefit us for our experiments that we're going to be performing for them. And we want to keep all of it as simple as possible, and everything is very symmetrical. All of the fins are, we're planning on having the same size, And I think the dimensions on them are about 1.5 feet tall by about 1.5 feet long.
So for our fins, the biggest thing we want is rigid enough structure, but also have them lightweight because we have a fairly rigid weight balance that we have to keep track of. And so we found a company called Rockwest Composites, and they are a distributor for Roacell, which is a manufacturer of foam core for aeronautics and aerospace. And we found their material lightweight foam with a thickness of only 0.21 inches. It's still thick enough to be rigid enough for our purpose, but it's also very lightweight. And that is very apparent when you see the density of 1.93 pounds per cubic foot. And with an area per fin of about 4 square feet, this will be a very key factor in our designs.
One of our design plans we have for the fins on the empennage is we want to embed motors in, for sure, the bottom one to start and see how this behaves. To do this, you can see in the picture, they have a circular cutout for the propeller that is going to be attached to the motor in this fin. The purpose of this is to add control and stability. So if you add a motor in the back and propeller, you can really get more control with the yaw and slightly more control with the roll. So if you think about it, if you have a propeller on the back side of that blimp and you add a lot of thrust to it, it's going to kick out the back side of that, whichever way you want. This is going to help with your turning radius and just having sharper turns. And then you also get a little bit of benefit from the roll of that. So if you think about it, if you put one of those motors directly below the blimp and added thrust to it, your blimp would start to roll. So we're going to get a little bit of that thrust or a little bit of that effect because it's still on that bottom plane, but just shifted slightly back. And again, we want to have as much control as possible. So we're going to start with 2 motors and 2 propellers on this. The propellers are most efficient in one direction they're facing. They can create thrust both directions when you spin them backwards, but it's just not as efficient. If we have 2, we can have one facing left and one facing right. This means we can quickly change which direction we're going.
And for part of our design solution for motors, we found motors with a motor velocity constant of 2,300 RPMs per volt. Essentially what that means is if we put 1 volt through the motor, we get 2,300 RPMs out of it, and that increases with every volt that we put in. These motors have a total weight of 24.6 grams apiece, and their maximum current that we can put through them is 17 amps.
Another problem we're tackling is which propellers we want to use. So some major factors that went into this decision were, again, the thrust that we need and the weight. With these propellers that we selected, we went with a 9-inch diameter and a pitch of 3.8 inches. If you think back to your design of machine elements class, that's similar to the TPI on a bolt, except in this case, it's inches per thread because it's such a high pitch. So if we rotate that propeller 1 time, it would travel 3.8 inches up or down, depending on how you think about it. And then for our thrust calculation, we know how much thrust we want because of our force of drag, because of how fast we want to go. So we take that thrust, consider our RPM, and then we can pick our diameter from that. This table on this slide is the experimental results from the vendor for this selected propeller that you see in the picture. So at 3,000 RPMs, we're going to be getting about 0.235 pounds of thrust from each propeller. We have 2 main thrust propellers. This gives us plenty of thrust for our design.
So our motor locations are kind of based off of what we've done research on. In the video that unfortunately didn't play earlier would have given a good demonstration of what this kind of looks like. So I'll start with the bottom part with our gondola. It's just a box for right now because this is something that we're going to be looking into in the next month or so. And we still have to figure out how to attach that. But on the inside is going to have all of our good stuff like our temperature sensors, our pressure sensors, and our battery and our Raspberry Pi coding stuff. This bar right here will be connected to a gear train that's connected to a servo motor on the inside that'll be coded by us. And all of that will be able to control the pitch of these. So, and later we'll get into the controller, which explains it more, but it'll change the pitch. We'll be able to turn these thrusters down, have you go down, or pull them up and have you go up. And then in the back with the empennage Ryan was talking about with the embedded motor, like you can see on the right, we're gonna have two in the back there to control our stability and have more effective turning. This is our controller. This isn't a set in stone controller. This is something that is more beneficial for this presentation. And this is something that we want our actual controller to be able to do. So in the top, we can see our rear propeller controllers. So this will control both of the ones in the back that control the yaw that Ryan was talking about. That will kick out the back end either way. That'll help the steering. The four buttons on the right will be the servo resets. So when it says servo reset up, we'll click this button. It'll flip the motors on the bottom completely at a flat 180 degrees. And then it will thrust down, sending our airship up. On the right, it'll reset horizontal, which will go flat, pushing us straight forward. And then the bottom one will have us flip. So we're making thrust up, and then it'll bring us completely down. The joystick on the right will control our pitch, which I was saying when you flip the front thrusters up or down, pushing that forward and backwards will angle that up or down, being able to lift you or lower you. And then the throttle and steering is on the left, and this will control the speed as much as the steering, because our steering is based off of the speed of the motors and the thrusters. So if you want to turn right, you will increase the speed in this and it will spin you to the right.
So this gets us into our transmitter. So right now we are kind of looking at the FlySky FSI-6. And so that gives us a radio frequency range of about 2.4 to 2.48 gigahertz. This leads into the control range of about 1,600 feet. This does depend on environmental factors, but because we will be conducting all of our experimentation inside, we will have no issues with this. It does also come with 6 channels. So with these 6 channels, depending on which channel we switch to, we can be controlling a different aspect of our lighter than air vehicle. So for example, if we want channel 1 to be the servos and channel 2 to be for the propellers, if we switch to channel 1, we can then control the servo position and control that pitch. And then if we wanted to switch to channel 2, we can then control the propeller speed. This also leads us into our testing locations. So right now, for some on-campus locations, we are looking at the barn, the S-Jack, which is the indoor track here, and then the animal science arena. These locations are large enough for us to fit our lighter than air vehicle in and do all the testing that we will need. Looking at the regulations of these buildings, we may have to look at some off-campus sites.
This is our bill of materials, and as you can see, we have a total cost of $600.25. But what we really care about is our budget weight, which is all the way on the right. And we have a total weight right now of 2 pounds. And that's including all of our propellers, our motors, our Raspberry Pi, and our transmitters, and our battery. And we specifically picked all of these to be as lightweight as possible. But our biggest weight contributors are our fins, which we chose that super lightweight material, and then our battery, which we needed the battery that could provide enough power for us to have run all 4 of our motors for about a test flight of 20 minutes. And then our wires are also contributing a big amount of weight, which may seem like a lot, but our motors are 8 feet back from our battery that's going to be in the center of our vehicle that's in the gondola.
And then here's our Gantt chart. This is mostly for this semester. Some of the things we want to get done before the end of the semester is to have a finalized bill of materials to order parts with, and then also get the physical hull from Aerostar so we can start testing physically at the beginning of next semester. Any questions?
For testing for, how many fins you want, where are you gonna do CFD simulation, like in Star CCM, or are you just gonna test it? You mentioned sticking them in different places in the blimp.
It's gonna be mostly physical testing, just because there are a lot of variables that would be a very complex simulation. And we decided to go the testing route because it would be more time efficient for us.
Sure, I get it.
Do you have any safety features for, like, let's say, if you lose connection, does it land itself or?
So when we do the indoor testing, we'll have it tethered and then likely have a person walking with it. And we'll have the person with the controls stay back just so it's more realistic, but then I had the blimp above me, I would walk around with it like a balloon, and if something went wrong, I could pull it back down.
Is the final goal then to not use a controller? Like, once it's completely scaled up to what Aerostar actually wants, will it be fully autonomous? Will you not have control in that?
One of our stretch goals is to look into the autonomous of that. Right now, we're just focusing on the handheld control unit. That could potentially change to a next phase of the project.
Those arrows.
No, I don't think so. It's just helium in there, so we'll just have to get the helium from either them or some third-party supplier, and then we'll fill it up ourselves. We talked about the first time we fill it up, they'll likely be with us so we can see the process and how to do it safely.
You guys said you have like the 6-pound budget kind of for your weight to make it like balanced. Is that something you want to end up having it be like neutrally buoyant so you can, so it's basically like not going up or down when it's not getting like thrust to it?
Sure. So our overall goal is to be lighter than air. But for the indoor testing of it, if we overfill it, it's going to end up in the ceiling. So when we do our actual test, it might be slightly lighter or less lighter than air. And then we'll add a little thrust to get it off the ground, but still be in control of it.
I guess, going back to your bill of materials there and your weight, did you, and talking about the tether that you're gonna connect your fins and everything to, did you include that into your weight?
No, not right now. This is our bill of materials only includes that weight on the bottom just includes all these items right here. So we still have those 4 pounds of work with for like our gondola we need to manufacture and the gear train for our servo motor that's going to spin our actual propellers.
Do you know the weight of those tethers?
No.
If you test it at the halftime of a basketball game with a advertiser's logo on the side, could you take that money you would make and increase your budget?
That's a good idea.
When you are doing your testing, will you simulate wind that they would experience at height?
That's not something that we're looking into right now. We're looking more of just the stability and everything. Aerostar's end goal is to actually not have any fins on it and have the aircraft be completely 100% efficient. Right now in our scope, we just don't have the time for that.
Are there any issues with roll? Because, you know, you got the fins aligned, so we control the pitch and we control the yaw. But what about roll? I mean, the back fin, if we try to run that, is going to change yaw. Right? Roll an issue, or is the gondola going to hold it vertical?
The gondola is likely going to be heavy enough to where it'll stabilize the sun, because the gondola will be at the center of gravity, and so that'll help offset the effects of that roll.
Yes, when you like, because you guys are creating a prototype, when they scale it, is that testing then gonna like be outdoor environment stuff then, or what?
Yeah, so Aerostar will likely take that over, maybe with like post undergrad students, just dealing with that. That's more of a following phase of this project,
Okay.
outside of our scale of view.
Do they have a specific gas you're using to make it lighter than air? I know you mentioned helium, but have you guys looked into any other gases that could actually increase your weight limit?
Helium is our best bet, and it's definitely our best bet because Aerostar uses that pretty exclusively. Really, the only other gas that we could use on this scale is hydrogen, and that's flammable, so we would like to not use that.